Hello, everyone. Hope that you're doing well. My students have asked me for a basic ABG interpretation video, so I'm trying to get that put together. I need it to be understood that we are going to go over in a few weeks acid-base balance, so there's quite a bit more to it than what I'm presenting in this video. But I understand that you're going to have some questions and you've got to provide some interpretation to it. So I thought I could go over just the basics to help you, be able to hammer down whether it's maybe a respiratory acidosis or metabolic alkalosis and so on. So first thing we got to look at is our normal values. So you got to know what constitutes an arterial blood gas. So we do have a pH value, a PaCO2 value, a PaO2 value, bicarb value, SaO2 for arterial saturation and base excess. You must commit to memory the normal values for those items. So pH is 7.35 to 7.45. PaCO2, your partial pressure of arterial carbon dioxide is 35 to 45 millimeters of mercury. Your partial pressure of arterial oxygen is 80 to 100 millimeters of mercury. Your bicarb is 22 to 26 milliequivalents per liter. SaO2 should be between 95 and 100%. The base excess should be plus or minus 2 milliequivalents per liter. So your pH is going to do one of a few different things for you. You're going to look at that first to be able to determine if your pH is normal. If it's normal, it's going to fall within that 7.35 to 7.45 range. You're going to determine if it's acidotic. If it's acidotic, you're going to be left of that 7.35 to 7.45 range. So it would be less than 7.35, that would be an acidosis. If it's to the right of 7.45, which is why I have it listed as such on this bullet point that goes directly across from the pH, will be an alkalosis. So any numeric value above 7.45 is going to be an alkalosis. So what we have to do now is look at the rest of that arterial blood gas to determine what the cause of that acid-base disturbance is, and you're going to determine that you're going to determine if it's a normal acidosis or an alkalosis by looking at your pH, and then we're going to assess the different components of the blood gas to determine if it's of a respiratory cause, if it's of a metabolic cause, and then later on we'll talk about the determination of if it happens to be of a mixed cause. So you've got to make sure that you can commit to those normal values. Absolutely have to know the normal values. 100% cannot do ABG interpretation without knowing the normal values. You must know those. It's also important to note that the PaCO2, partial pressure of arterial carbon dioxide, is the respiratory component. Eventually, you will get into establishing whether there's a degree of hypoxemia associated with that. So for the purposes of, once I get to it in cardiopulmonary anatomy physiology, I will ask you to determine what the acid-base disturbance is, determine if it's compensated, partially compensated, or if it's uncompensated. And then you will also have to provide a degree of hypoxemia associated with that. So you'll be looking at the different components. For the purposes of this introductory video, we're going to, for the most part, focus on our pH, our PaCO2, and our bicarb. I think that'll help us establish some relationships, and then hopefully we can dive further into acid-base balance a little bit later on when we get to there in class. So absolute terms that you've got to know, in addition to those normal values in the previous slide, that you've got to know. We must know what hyperventilation is. We must know what hypoventilation is. We must understand that hyperventilation will result in a decrease in your PaCO2. That's your partial pressure of your carbon dioxide. So hyperventilation results in hypocapnia or hypocarbia. Those two terms are medical terms that describe that you have a PaCO2 that has been lessened. So you have a lower PaCO2. Hypoventilation results in an excess of PaCO2. So if someone hypoventilates, they're not breathing effectively to remove their PaCO2, so that PaCO2 value is going to climb, or they're going to become hypercapnic or have hypercapnia, or they're going to become hypercarbic or have hypercarbia. Both of those terms mean the same thing. Hypoventilation results in hypercapnia, hypercarbia. Hyperventilation results in hypocapnia or hypocarbia. That's going to be important for you to remember as well. Absolutely have to make sure that you remember that, because we're going to talk about some relationships on the next slide. So when we talk about acid-base disorders, we could have either a respiratory acidosis or a respiratory alkalosis. You could have a metabolic acidosis or a metabolic alkalosis. It is possible in some situations you can end up with a combined or mixed acidosis or a combined or mixed alkalosis. And we will discuss that, maybe not in this presentation, but later on once we get there in class. You'll also notice that I've color coded these top, and I just left it purple down here, but nonetheless, respiratory acidosis is purple, while the metabolic alkalosis is purple. Respiratory alkalosis is blue, while the metabolic acidosis is blue. The reason I did that is because you are going to have to determine if there is some compensation. So ultimately, we understand that as far as the respiratory component of the blood gas is concerned, and remember that is the PaCO2, we will have adjuncts of therapeutic modalities, whether that's a non-invasive ventilator, whether that is invasive ventilation. You should be able to acquire direct control over that patient's unit ventilation to augment that PaCO2 to go up or down. We'll talk more about that in a moment, but the reason I color-coded these as such, because if you allow the body to compensate solely without any type of therapeutic intervention, if you allow the body to compensate, if you have a respiratory acidosis, the body will try and fix itself with a metabolic alkalosis. On the flip end of that, if you have a respiratory alkalosis, the body will try to fix that with a metabolic acidosis. If the body presents with a metabolic alkalosis, it will try to fix itself with a respiratory acidosis. If the body presents with a metabolic acidosis, it will try to fix itself with a respiratory alkalosis. That's why I've color-coded those, because I think that's helpful when you think about the degree of compensation or if there is compensation that occurs. And we'll talk more about that momentarily. But again, this is stuff we've got to know for the determination of arterial blood gas interpretation. So we'll transition to the next slide. In addition to normal values and terms, there are relationships that we absolutely have to make sure that we remember and can apply those to our arterial blood gas interpretation. So we must understand that the pH is inversely related with the PaCO2, partial pressure of arterial carbon dioxide. So if PaCO2 goes up, pH will go down. If PaCO2 goes down, pH will go up. So with a respiratory acidosis, that would mean that your PaCO2 goes up and it drives your pH down. With a respiratory alkalosis, that means that your PaCO2 has gone down and it has driven your pH up. Must remember those relationships. With bicarb, pH varies directly with your bicarb. So if bicarb goes up, it will take pH up with it. If bicarb goes down, it will take pH down with it. So if you have a metabolic acidosis, bicarb has gone down, your pH has gone down with it. If you have a metabolic alkalosis, pH has gone up, bicarb has gone up, and it has taken your pH up with it. Got to know these relationships. And these relationships, you can apply those not only to interpreting the blood gas, but also to help you determine the degree of compensation as well. So we'll continue to look at those momentarily. So I have brought back the normal values. pH is 7.35 to 7.45. I'm repetitive because it's important. You need to know those. PaCO2 is 35 to 45 millimeters of mercury. PaO2 is 80 to 100 millimeters of mercury. The bicarb 22 to 26 milliequivalents per liter. SaO2 is 95 to 100%. And our base excess is plus or minus 2. So that can be a positive number or a negative number. And we'll talk more about that a little bit later on as well. But for the purposes of what we're doing today, we're going to focus on the pH. Are we normal? Are we acidotic? Are we alkalotic? And then we're going to focus on the PaCO2, which will be the respiratory cause potentially of the acid-base disturbance. Or we'll look at the bicarb, which would be the metabolic or renal cause of the acid-base disturbance. So if I look at this first blood gas right here, you'll notice that those values fall directly in the middle of all of your normal values. So 7.40 with a PaCO2 of 40. And it's important to note that these are going to be listed in that order: pH, PaCO2, bicarb. So whenever I have these on the subsequent slides, it's going to be listed pH, PaCO2, followed by the bicarb. So it's pH, your respiratory component, which is the PaCO2, and then your bicarb, which is the metabolic component, HCO3. So we will look at our interpretation that in that realm. So if the very first blood gas listed here at 740, 40, and 24, the first thing I'm going to do is look at that pH. pH is normal. Now, if it's normal, there's not anything that pushed it out of the way, so I'll just look at the rest of it. So my CO2 is normal and my bicarb is normal, so I would be okay to call this a normal ocular blood. The next blood gas down, I'm going to look at this. I have a 7.30. That is less than 7.35. So that's an acidosis. Now I have to figure out, why is there acidosis? So if I'm looking at the 7.30, the 50, and the 24, I've established that I have an acidosis. Now I need to understand if this is a respiratory acidosis or if this is a metabolic acidosis. Go back to those relationships we talked about. CO2 will be inversely related with your pH, while bicarb will be directly related with your pH. If I look at this PaCO2 value, it is above normal. It has increased. I also have a decrease in my pH. That is likely the causative factor. I'll take a look at my bicarb. My bicarb is unchanged. It's unmoved. It's still 24. So I am looking here at a respiratory acidosis. Specifically, it's uncompensated respiratory acidosis, but we'll look at that here shortly. But this is a respiratory acidosis because your CO2 is above normal, your pH is below normal on the acidotic side. So this is a respiratory acidosis. You look at the blood gas below there, 7.50, 30, and 24. I now have a pH that is out of range, but it's out of range on the alkalotic side. So it's above 7.45. So this is an alkalosis. Now I have to determine what the cause of that alkalosis is. So I can assess the respiratory component of the blood gas, which is the PaCO2. PaCO2 is less than 35 to 45 millimeters of mercury. That CO2 has gone down. But if I remember the inverse relationship, CO2 goes down, it drives pH up. That's exactly what's happened here. If I take a peek at the bicarb, my bicarb has stayed right there where right in the middle. So that's not the causal factor. So I am looking here at a respiratory alkalosis. A lower CO2 has driven my bicarb up. So now this slide has focused on the respiratory causative issue for the acid-base disturbance. So now let's take a peek at the same stuff. Just maybe view the metabolic issues that was potentially going on. So here, we're going to do some additional practice, and just for the sake of repetition, because it's important to know the normal values. pH is 7.35 to 7.45. Above 7.45 is an alkalosis. Below 7.35 is an acidosis. PaCO2 35 to 45 millimeters of mercury. Above 45 is hypercarbia or hypercapnia. That would mean the patient's hypoventilating. If the PaCO2 is less than 35, that's hypocarbia or hypocapnia. That means the patient is hyperventilating. Again, terms still we need to make sure we know. PaO2 80 to 100 millimeters of mercury. Bicarb 22 to 26 milliliters equivalent per liter. SaO2 95 to 100% with a base X left plus or minus P. So we'll look at the very first blood gas. Very first blood gas, everything runs right across. So assess the pH first. It's normal. My CO2 is normal. My respiratory component is normal. My bicarb, the metabolic component, is normal. So that first one is a normal ABG or a normal blood gas. Now we'll scoot down to 7.28 CO2 of 40 with a bicarb of 19. The very first thing I looked at is that pH. I determined that pH was acidotic. It's less than 7.35. Now I have to look at the respiratory and the renal or metabolic component to determine what the causative factor is. My CO2 stays put at 40. So it hasn't moved. So that's not going to be the reason why my pH is less than it is, or as low as it is. But if I look at the bicarb, and I remember that my bicarb has a direct relationship with pH. If bicarb goes down, it brings pH down with it. Then here I'm looking at a metabolic acidosis. I have an acidosis, and it's the cause of it is the metabolic system. So it's a metabolic acidosis. 19 is less than 22. That is a metabolic acidosis. So I'll come down to the next blood gas, 7.50, 40, and 30. PaCO2 is 40. That bicarb is 30. If I look at the pH first, I have an alkalotic pH. I have to determine the cause of that alkalosis. It's not the respiratory component. That value is normal. That bicarb is elevated. If I remember those relationships, if bicarb goes up, it brings pH up with it. This is a metabolic alkalosis. Now, I should have prefaced all of these. I have not run the Henderson-Hasselbalch equation on this, so the way I'm placing these numbers just for the sole purpose of establishing the relationship. I'm not saying that these are accurate blood gases by any means. The interpretation is accurate based on what we're looking at, but as far as if these are actual feasible blood gases, so don't get lost in that. Don't say, well, the HH equation says that this isn't possible. It's possible that would happen. But I'm putting these numbers in here for the sole purpose of trying to establish the relationships and seeing how things move. So now if we transition to our compensation piece of items. So all I've done now is I've taken the blood gases that we've gone over, and we're going to talk about them individually. So on both sides of the slide, I'm going to have our respiratory problems on the left side, metabolic problems on the right side. So we will begin to discuss compensation, and we'll take a deeper dive into that on the next slide after we get finished with it. So if we look at our normal blood gas, there's no compensation needed. That's essentially what a perfect blood gas would look like. If we come down to where the respiratory acidosis piece is, so let's examine that. We have an acidosis, we have a high PaCO2. Those relationships are perfect. So, or I'll say perfect, but it matches up. CO2 has gone up, our pH has gone down. We have a respiratory acidosis. So if the body was going to work, now, don't get terribly confused. We've not started mechanical ventilation yet. We've not started non-invasive or invasive ventilation. It's all be mechanical ventilation and probably pressure ventilation. We could 100% fix this without by manipulating things, but that's a conversation for a different time. What I'm talking about over the next slides, the next few things we're talking about, is if we allow the body to fix the acid-base disturbance. So this is compensatory mechanisms that come into play. So if you remember those relationships, if CO2 goes up and pH goes down, in order for the body to fix this, the bicarb would have to begin to creep up so that it would, assuming that your CO2 remained unchanged, the bicarb would have to come up to bring the pH up to it so that you could have compensation. So a respiratory acidosis will have renal compensation by the production of more sodium bicarb or bicarb. Look at the next gas down, 7503024. Look at the blood gas, or look at the pH first. It is alkalotic. We have established, because of those inverse relationships, a low CO2 drives the pH up. So this is indeed a respiratory alkalosis. But if I wanted to look to see if the body was compensating for that, if I have a respiratory alkalosis, the body would have to compensate for that by causing a metabolic acidosis. So this bicarb number would have to begin trending down to bring that pH down. Flip over to the next slide. And we're going to look at these in a little bit more detail on the next slide. Let's look at the next column over. So again, we have a normal blood gas at the top. The second blood gas, 7.28, we established that it is an acidosis. We determined previously already that the causative factor because of the direct relationship that bicarb has with pH. With bicarb, our bicarb is uh, less than normal, so our pH is lower, so we have a metabolic acidosis. So now we have to think about how could the body fix this? Well, remember those relationships with the respiratory system. If the CO2 were to go down, it would take the pH up. That's exactly what would have to happen if we allow the body to fix this. The CO2 would have to begin to go down, and that should hopefully help drive the pH up, assuming that bicarb stays right where it's at. Look at the next blood gas line, 7.50, 40, and 30. CO2 is 40, bicarb is 30. The first thing we look at is the pH. It is a metabolic, or excuse me, it is an alkalosis, and we have to determine the cause. Well, we've already, on the previous slide, determined that this is a metabolic cause, so it is a metabolic alkalosis that we will show. Bicarb has gone up, it's brought pH up with it. So now we have to look at if the body were to try to fix this, how would it do it? And you have a metabolic problem, so you're going to look to the respiratory system to fix the issue. So that's also going to be important. Identify the problem with your acid-base disturbance, and then if you're trying to assess for compensation, the other system is going to compensate for them. So we have a metabolic alkalosis, and in order for this pH to go back closer to normal, that pH is going to need to be reduced. How is the respiratory system going to do that? By allowing that CO2 to climb. So if the CO2 were to go up, assuming that the pH, assuming that the bicarb is unchanged, and that's going to begin to drive the pH down. So let's look at it. It's a lot of talking on a few words here. So let's look at it. Working with, so what I've done is I've grouped respiratory issues together, or respiratory acidosis issues together, those in purple. Respiratory alkalosis issues here together in green. Metabolic acidosis issues, I'm going to assume that's blue. Maybe it's a different color, but we call that blue. And then metabolic alkalosis issues grouped together here in black. And I should have, so these three numbers should go along with that. They're blue, but they should go along with black. Oh, I missed that one. I was color coding. So let's take a peek at a respiratory acidosis first. We know that normal is 7.40, so that's pretty much a perfect looking blood gas. So I've got those highlighted in yellow at the top of each column. Start off with what constitutes a respiratory acidosis. So remember your relationships. CO2 and pH are inversely related. Bicarb and pH are directly related. So I first look at this blood gas or this pH, and I determined that it is an acidosis. I have to determine what is the cause of that. The relationships speak for themselves. CO2 is up, pH is down, bicarb is normal. Therefore, this is a respiratory acidosis. Specifically, this is an uncompensated respiratory acidosis. Now, how do you know this uncompensated? If the blood gas is compensated, if it's fully compensated, your pH value is back within normal limits. And remember, normal limits is 7.35 to 7.45. If it is compensated, your pH is back within that 7.35 to 7.45 range. If it's partially compensated, you identify the problem for the blood gas. So in this case, it's a respiratory acidosis. So if I need to determine if there's partial compensation, I have to look at the other system to see if it's moving in the direction that would help bring my pH back to within normal range. So we've established here in the first purple set of numbers that this is a respiratory acidosis. If I look now at those numbers, I have 7.33, assuming the CO2 stays the same at 50. My bicarb has now come up to 27. Remember the relationships. It's still a respiratory acidosis because the inverse relationships between your CO2 and your pH drives that pH down to an acidosis. Very good. But notice from the first blood gas to the second blood gas that pH has now come up a little bit. 7.33, it was 7.30. Notice the difference in the bicarb from the first blood gas to the second blood gas. Now from 24 to 27. That brought the pH up a little bit. So because there is movement with the bicarb now, this is a partially compensated respiratory acidosis. It's still a respiratory acidosis, but because now the renal system or the metabolic system is working to buffer the system or working to compensate, it is a partially compensated respiratory acidosis. Now we take a peek at the next one down. It's 7.36, 7.36. So like we mentioned, it's 7.36. The CO2 has remained unchanged at 50, and we have yet another change in the bicarb. It's a respiratory acidosis because the high CO2 has put my pH on the acid, down toward the acidosis. With this one specifically, we're now back within that normal range, but we are on the acidotic side of normal. 7.36 is on the acidotic side of normal. So the CO2 is likely the cause of the reason for why the pH was low. And if we look here, our bicarb has now increased an additional 2 milliequivalents per liter, which would result in bringing that pH up to 7.36. So although these two values, my CO2 and my bicarb, are out of normal range, they are working together to fully compensate this blood gas by bringing the pH back into the normal range. This is a fully compensated respiratory acidosis. Now we take a peek at 7.50, 30, and 24. We established already on previous slides that this is a respiratory alkalosis because of the factors below CO2, it drove the pH up. Looking at the blood gas down below, 7.47, 30, and 21. If we, and just assuming these are all on the same patient and we're allowing the body to compensate, notice that I'm leaving the CO2 in the same range with the only changes being made to the metabolic system. So we have a respiratory alkalosis that we're looking at here with 7.50, 30, and 24. Next blood gas down, 7.47. CO2 is still 30, still the respiratory alkalosis, but there's partial compensation now because that bicarb has moved the direction it needed to in order to start bringing that pH down. So this is a partially compensated respiratory alkalosis. 7.44 CO2 at 30 and 18. So now we are compensated because we're compensated because now that, and we're fully compensated because that pH is within that 7.35 to 7.45 range. The CO2 stayed where it was, but the bicarb has now reduced low enough to bring that pH back down within normal limits. Hopefully that makes pretty good sense. Compensation is important to understand. Now we'll switch over to the second column. Still looking at a normal blood gas at the top. We have 7.28, 40, and 19. We established from the previous slide that this is, on one of the previous slides, that this is a metabolic acidosis. Acidotic pH, causative factors below bicarb. Now we'll look at the next blood gas down. So, we have a pH of 7.32. The PaCO2 now is 34, while the bicarb is 19. This is still a metabolic acidosis. The low bicarb has brought down the pH, so the direct relationship is still there. What does the respiratory system have to do to fix that? Well, the respiratory system now has to remove more CO2 because the inverse relationship, if the body can get the CO2 down, it should bring the pH back up. And that's what we're seeing here. But because that pH isn't between 7.35 and 7.45, this is the partially compensated metabolic acidosis. Now, if we look at the next one down, 7.36, 30, and 19. 7.36, 30, and 19. The pH is within normal range. It's still on the acidotic side of normal. All right, I did have a call to the recording, and I apologize for for having stepped away. Um, but nonetheless, I'm just gonna start over with this call because I don't remember where I was, uh, what, where I was at uh, the explanation. We're starting on this side, 7404024 normal blood gas. We established already on previous slides at 7.2840 and 19 and those are metabolic acidosis because the bicarb has decreased and it's brought down the pH with it. So now we're looking for compensatory mechanisms. Does it cause no compensating, what have you? So remember, if you have a metabolic problem, the respiratory problem is going to be hopefully make some changes to help save the day and bring the pH back within normal range. So if we look at the next blood gas down 7.32, PaCO2 of 34, and bicarb of 19, still a metabolic acidosis, but now that bicarb, the PaCO2 has moved in the direction to begin bringing that pH up. So the bicarb, the PaCO2 rather, the bicarb is low, so the PaCO2 now has to go down with the inverse relationship with CO2 and pH. CO2 goes down if you hope to help start bringing the pH back up. So notice with a further decrease in the CO2 in the next blood gas down to 30, that has now brought that pH up to 7.36, and that is within our normal range. So that is a compensated, fully compensated blood gas. The respiratory system has now been able to compensate. The respiratory system has now been able to compensate that low bicarb, and now our pH is back up to the normal. So that would be a fully compensated metabolic acidosis. I'm going to come back to this in just a minute and kind of talk about, what we talk about why we look up the body this thing. So now we look at, and again, this set of numbers should have been in black. So I apologize that they're in blue, but they should be in black. 7.50, 40, and 30. We established that because that bicarb is elevated, we brought the pH up with it. So this is a metabolic alkalosis. That the bicarb is the reason why we have the pH out of range. So we're going to leave that bicarb at 30 over the next few blood gases to try to help hit home the compensation piece of that. So you have a metabolic problem. The respiratory system is going to be the compensatory mechanism. So now our pH is too high when we look at 7.50, 4, or 40 and 30. That pH has now come down to 7.47. Why did that pH come down to 7.47? Why is this now partially compensating metabolic alkalosis? Still metabolic alkalosis because the bicarb is why that pH is high. But now if we look at the respiratory component is compensating because now the CO2 is moving in the direction to help bring, and remember the inverse relationship of CO2 and pH. CO2 goes up, it brings pH down. So now as CO2 creeping up, it's beginning to bring that pH down. So this is a partially compensated metabolic alkalosis. Now we look at the next blood gas, 7.04. PaCO2 is 50, and a bicarb is 30. This is a fully compensated metabolic alkalosis. We're still, although the pH is normal in 7.35 to 7.35 to 7.45 range, it's on the alkalotic side of normal, and that is most likely the cause of it. That is the cause of the reason your bicarb being 30. So in order for the respiratory system to compensate for that, the patient had to begin to hypoventilate enough so that CO2 is climbed high enough to bring this down. Now, obviously, that in these scenarios, it's not advantageous to start let the body fix it. So, for instance, we come up here to a metabolic acidosis. You all probably heard of a diabetic ketoacidosis patient. So they're going to come in, they're in a metabolic acidosis with us. The bicarb is going to be low in order to compensate for that. In the clinical presentation you'll have for those patients, they're going to be breathing fast and deep. And the reason they're breathing fast and deep is because they're beginning now to try to blow that CO2 down to bring that pH back up. They're only going to be able to achieve that for so long. They're going to tire out. And when they tire out, they're going to quit breathing. And when they quit breathing, that CO2 is going to climb. That climb in CO2 is now going to let the pH fall. And that would be a situation where you have this combined and mixed blood gas. So I'm hopeful that this helps break it down and make a little bit more sense. You all let me know. Thank you for your time and attention.